Okay, so yeah, we're going to talk about computing some four-manifold invariants today. Okay, so what we're going to talk about is the Sutured Floer mixed invariant. So this is due to Ozsváth and Szabó, and it takes the form of a map. So if X is a closed-oriented four-manifold, there's a map phi sub X from the set of spin C structures on X to, for our purposes, it'll be the field with two elements. Conjecturally equal to the Seiberg-Witten invariant. I think everyone believes that's the case. So it's a map from spin C X into F, and so it sort of is convenient. One way to encode this, it's convenient algebraically to encode this into a polynomial. So what we can do is we can just pick a basis eta. So pick a basis eta, eta 1 through eta n of h upper 2 x with r coefficients. And then I want to create a polynomial just by sort of summing over all spin C structures, but weighting them by powers of related to this basis. So I want to encode this algebraically. So this is the basis of two forms. This will be the sum over spin C structures of phi x s. So this is phi x evaluated on s times. So I'm going to encode it with n variables. So it's a polynomial in n variables. And so I want eta cup the spin C structure minus just some base spin C structure. Just we pick any arbitrary spin C structure we'd like, S0. And then we're going to evaluate it on the fundamental class. And so we want an n variable polynomial, a polynomial in n variables. So we'll do this for each element of our basis. Sorry, this is eta 1. So this will be Tn to the eta n cup s minus s naught evaluated on the fundamental class. Okay, so this is the invariant we're going to study, and what we want to study is a variation of knot surgery. So what is knot surgery? So this is spectacular construction due to Fintuschel and Stern in the 90s. I think their paper was published in 98. And so if you have a knot K in S3 and a four-manifold containing a torus. So if we have a K and a torus, we want a little. We need to assume something about this torus. We need to assume that it has self-intersection number 0, and that I'll just say T, the class is not 0. Let me just say with. For our purposes, we don't want it to be 0 in homology with R coefficients. And then the statement is slightly different than what Fintuschel and Stern, just slightly different than what Fintuschel and Stern proved. Oh, wait, sorry, I forgot to tell you what the four-manifold is. So Fintuschel and Stern constructed this four-manifold xk, and it's defined as the union of X minus the neighborhood of the torus, a union along T3 of S1 times S3 minus the neighborhood of K. Oops. Sorry, let me write this a little better. And so we want the meridian of the torus. So we want to glue these together so that the meridian is glued to the longitude. the meridian of the torus is glued to the longitude of the knot. So I'll say a point times a longitude. Okay. And so what did Fintuschel and Stern prove? Fintuschel and Stern, they computed the effect of this operation on the Seiberg-Witten invariant. What they showed was that the Seiberg-Witten invariant, I'm just going to use this notation up here. They showed that the Seiberg-Witten invariant of xk with a basis, so when we surgery along k, do this knot surgery, they showed that the effect was just to multiply by the Alexander polynomial of k in one of the variables. Oh, and I forgot to assume something. Forgot to mention that, let's assume that, let me just put it over here. We want to assume that the integral of t over eta 1 is 1, and the integral of t over the other etas is 0. So this is t1. What did I say? Oh, yeah, thanks. Yes, you're right. Thank you. Thank you. Okay. So this is sort of a spectacular result in low-dimensional topology that I think everyone is really familiar with. And so I'm going to describe a generalization of this today. So there's sort of a variation on this knot surgery operation that you can do if you instead of just a knot, I'm going to take a self-concordance of a knot. So we're going to call this concordance surgery. So I want to take a knot in S3, but I want to take a self-concordance of K. So I'm going to take C, this is an annulus inside of the interval times S3 is a self-concordance of K. So in pictures, we have, this would be I times S3. So this is the I direction. And then inside of here, I have a self-concordance of a knot. So this would be C. Right, and so what we can do is if we glue up, oh, and this annulus has the same knot in both boundary components, so we can glue it up to get a torus inside of S1 times S3. So we can glue up to get a torus. Torus TC in S1 times S3. So in this picture, we'll call this TC. Well, we can perform a sort of analog of this knot surgery thing. We can define the four-manifold XC. This is going to be the union of X minus the neighborhood of our torus. Union along T3, it'll be S1 times S3 minus a neighborhood of this concordance torus. And we're going to glue those up in the same way. We want to glue up the meridian of this torus in X to basically a point times a longitude. So we want, it's the same thing. Meridian should glue up to a point in S1 times the longitude of K, of the slice K. Sorry. This is a slice, and the slice is K. Okay, so we get this four-manifold. And so what we're going to talk about today is the mixed invariant of this four-manifold X sub C. And so let's see. The theorem, so this is due to Juhas, and Anders Juhas and myself, we proved that the Sutured-Floer mixed invariant phi sub x, this polynomial one weighted by these homology classes, is equal to phi x eta times a graded Lefschetz number in the variable t1 corresponding to the torus of a map on not Floer homology, which I'll write fc from h of k hat of k to h of k hat of k. And so so this is the graded Lefschetz number. It's graded in the Alexander grading, so we could instead write this as the sum of I in Z of the Lefschetz number of FC restricted to the Alexander grading, the Ike Alexander grading, H of K hat Ki times T1 to the I. Oh, I forgot. What? Sorry. Oh, thank you. Yeah, thank you. Excellent. Good point. XC. Yeah. So this is the theorem. Okay. So right. So I guess one thing I want to mention, or I forgot to mention this before, but this theorem about, so Fintushel and Stern proved this not surgery for the Seiberg-Witten invariant. And actually, Tom Mark proved this theorem for just for not surgery for the Sutured-Floer mixed invariant. And both proofs were pretty similar. So Fintushel and Stern, Fintushel, Stern, and I'll just say Tom Mark proved it. Mark's, I forgot to mention it up there, but Mark's proof, their proofs were similar conceptually for the not surgery formula for Seiberg-Witten and this mixed invariant, I'll call it phi x still, used the logarithmic transform. So the logarithmic transform is a way of sort of doing surgery where you're going to take out something that has boundary T3 and then glue it in again with a diffeomorphism of T3. And so what they did was they related the log surgery to the Skine exact, or the Skine relation for the Alexander polynomial. So both related the logarithmic transform to the Skine relation for the Alexander polynomial. And so they showed that when you do this logarithmic transform, you kind of recover the Skine relation for the Alexander polynomial, and then since the Alexander polynomial is determined in some sense by these by the Skine relation and some normalization, and they can conclude that it's that the Seiberg-Witten invariant changes. But our proof is much different. Our proof, I mean, there's not really a known Skine relation for this Lefschetz number. It's not really clear how you'd pull that sort of strategy off. So we'll describe today, I guess, how we did that. Okay. All right. So the first thing I want to say, I want to talk a little bit about this concordance map FC. So FC, this concordance map. The construction is due to Juhas. Is due to Juhas using his Sutured Floer homology TQ of T. And I want to say something that really this concordance map also depends on a decoration on the concordance. So it depends on a choice of arcs, A on C. So these are, let me just draw a picture. So this is a pair of arcs. So if this is our concordance, this map will depend on a choice of two arcs that sort of run along the concordance. So I'm kind of thinking of this twisting. I mean, you could encode this in just one arc, but the natural framework is to have two arcs. But it turns out that the Lefschetz number doesn't depend on this, the choice of arcs. It's independent of that. And that's actually fairly easy to see. Just can give you a very fast proof of that. FCA, let me just say the graded Lefschetz number of this map is independent of A. And that's actually fairly straightforward to see using some of this link Floer homology technology. Because if A and A prime differ by a twist, then actually f of C A prime is equal to 1, the identity plus phi, a map C times f of C A. So what are phi and C? We'll not get into the details, but this is a consequence of this diffeomorphism map. There's a computation of this diffeomorphism map which twists the knot in a full loop. And this is a consequence of a theorem due to Sharkar. And what are phi and psi? Well, we don't really need to know what their actual form is, but they have some simple properties with respect to the concordance map. For instance, phi squared is psi squared is 0, and phi psi and FCA all commute. So we see that FCA is FCA prime, the one that's obtained by another twist, is FCA plus phi times psi, phi composed with psi composed with FCA, but that last term is nilpotent. It squares to 0, so it's going to have trace 0. So this Lefschetz number doesn't depend on the decoration. It's independent of the decoration. Let's see what. Okay, so now I'm going to describe how sort of our strategy for computing this thing. Yes, I can read this up. Well, this XC is a union of two things. So what we're really going to try to do is we're going to use the composition law for the Sutured-Floer map, and we're going to basically XC differs from X by just this part on the right, like S1 times S3 minus the neighborhood of this concordance torus. The original manifold X is just X minus the neighborhood of T union S1 times S3 minus the neighborhood of S1 times the unknot. So we can, one thing that, the way that we would try to do this is we would compare the maps on Sutured-Floer homology. So let's say the plus flavor of Sutured-Floer homology of S1 times S3 minus the neighborhood of this this torus TC, and we would try to compare this to F plus of S1 times S3 minus the neighborhood of S1 times the unknot. And these are both maps from HF plus of the 3 torus to HF plus of S3. So if you really wanted to get your hands dirty in how you would compare the, we're not going to go into using the composition law, but for our purposes, it sort of is sufficient to compare these two maps. The mixed invariant is defined using the cobordism maps. And so in this case, it sort of is sufficient to consider it on the plus flavor of Sutured Floer homology. But this actually isn't really a convenient way to do it, the way I've written it here, because HF plus of T3 is like a little too big to really compare the maps. It's hard to compute it on this version of HF plus. So instead, what we want to do is we want to use the twisted version of Sutured Floer homology. Which will, the formula will start, oh wait, I don't want to erase this, hold on. Let's leave this up. Erased. Okay, so what we're actually going to do is, it's better to compare these two maps. Let me actually make some notation. So, I'm going to call this W sub C, and I'm going to call this W sub U. And they're both manifolds with boundary equal to T3, and they go to S3. So sort of the crux of this whole problem is to compute these two maps, or compare them at least. So a better thing to do is actually to use twisted coefficients, twisted by a 2 form on your manifold. The way I've drawn this, the way I've written this up here, these are just sort of the absolute groups. We don't, there's no twisting, but you can sort of encode a cohomology class into the Sutured Floer groups, which makes this computation much more convenient. So instead, what we're going to compare is we're going to compare this WC, and we want to twist it by a class. It's simple to describe it. It's going to be the Poincare dual of a point times a Seifert surface. So this is a Seifert surface for K. Seifert surface for K. And then we're also going to compare these maps. We're going to compare this one for the concordance torus complement to the one for the unknot, the S1 times unknot, also twisted by a similar class, but we want to do the point times a Seifert disk for the unknot. And so these both go from HF plus of T3, but now we have to use twisted coefficients in the domain. And so we're going to twist by the restriction of these two classes to T3, which we'll just assume is a fixed class. I'll just write eta for that. And then it'll go from this to HF plus of S3. Of course, there's no non-trivial 2 forms on S3, but it still has, so it's twisted by the trivial 2 form, but it still has a factor of the, I mean, it's still, you still have to use the Novikov ring. And so these are what we're going to compute. We're going to compare these two maps. Basically, the reason that this is a lot easier to do is that HF plus of T3 is pretty complicated. I mean, it's reasonable, but it's a lot more complicated than when we twist. But sort of the key fact is that this is actually just rank 1 over the Novikov ring. This is just isomorphic to the Novikov ring and with trivial U action. And so this fact is sort of what lets us do any of the computations. And HF plus of S3, this is just like a tower of Novikov rings. And the U action moves from one to the other. And so we have this map from here to here, and our goal is to compare them. And actually, what we're going to prove, or what I'm going to describe in this talk that we're going to try to prove, is these maps can actually be compared more easily than this map without the twisted coefficients. And what we're actually going to show is that one is just multiplied by the Lefschetz number. So let me say f plus wc twisted by this class Poincare dual of a point times the Seifert surface for k. This is equal to f plus w unknot Poincare dual of a point times Seifert disk times this Lefschetz number. And so I'm just going to put t, this will be the variable from the Novikov ring, t of this concordance map. So this is what we're going to describe how to prove. And if you just use think about it and use like the composition law for Sutured Floer homology, that would recover the main theorem on the mixed invariant. Okay. The eta. Oh, that's just, so these two classes, this one and this one, they have the same restriction to the torus. So I just wrote eta for their common restriction. Okay, and so to compute this map, we want to show it's the Lefschetz number on not Floer homology. So we what we need to do is we need to relate this cobordism map for this concordance complement to the Lefschetz number on this map on not Floer homology. In doing that, we have to relate this map on the torus complement to not Floer homology somehow. So that's, this is just a setup, but now we actually have to prove the thing, describe this connection. Okay. All right, and so one observation is that this whole problem, this whole solution is dependent on the fact that this is rank 1 over the Novikov, or rank 1, yeah, that HF plus of T3 with twisted coefficients is rank 1. And so what we're actually going to do is on either of these, on this torus, let's see, on TC, what I want to do is I want to pick a pair of curves that go around. I wonder if this is better colored. We'll use red. So I'm just going to pick a pair of curves like this on TC. And also you can do the same thing on S1 times the unknot. We can pick a pair of curves that kind of go around like this, that are parallel. And this is a dividing set on a torus. And so, well, what is a, well, the boundary of a neighborhood of TC, this is basically just S1 times TC, or isomorphic anyways. And similar for this torus, S1 times an unknot. And we have a dividing set on this torus, and so that gives you an S1 invariant contact structure. So the dividing set induces an S1 invariant contact structure on on boundary of a neighborhood of TC. An S1 invariant contact structure, let me write CC on here. And similarly, we get an S1 invariant contact structure on a boundary of the neighborhood of this. And I'm going to, since we're identifying the boundaries of boundaries of neighborhoods of both of these surfaces, I'm just going to write C for the common contact structure. So we have an S1 invariant contact structure on T3, which is identified in the boundary, under the diffeomorphism of the boundary of these neighborhoods. And so there's a contact element in Sutured Floer homology. There's a contact element C of C, and this sort of naturally lives in hat of HF hat of T3, but I can put it in the module with twisted coefficients. There's a version with twisted coefficients, and I guess I should actually call this two form. I'm going to call this eta of T3. So that's the common restriction. Let me just. Well, it's the same eta as up there. So we have this element in hat. It's HF hat of T3 in here, and there sort of is a map from HF hat to HF plus. It's just there's sort of a canonical map that you get. There's a long exact sequence involving the U action on HF plus and HF hat. And so there's a map that looks like this. And basically, by definition, there's also a contact invariant in the plus version. And basically, by definition, the invariant in hat is mapped to the invariant in plus. This is basically just the construction of the plus invariant. So we have this element in here. And so what we're going to do is we're actually going to show, going to evaluate these maps, these cobordism maps on this contact element. So what we're going to show is we're going to show that f of this concordance map, we're going to show actually that the hat map on this point, Poincare dual of a point times S, evaluated on this element, this contact element, is equal to the map here, evaluated on the Poincare dual of a point times a disk, the contact element of C, times this Lefschetz number. Okay? Oh, yes. The graded Lefschetz number. And so if we can show it on the hat version, well, then we just include it into the plus version, and we get this inequality for the plus maps. And then what we'll also see is that this map is non-zero. I mean, that'll be sort of obvious from our computation, or that this map evaluated on this contact element, that'll actually just be 1 in the Novikov ring. And so using the fact that HF plus of T3 is just rank 1, that implies that the maps are actually equal. So that's going to be our strategy. So what are we going to show? We're going to show this equality, and then just along the way, it'll just be obvious that this is non-zero, and that'll imply that the maps on plus satisfy this equation. So that's sort of the goal for today. This is where we're going. So let's just say we're going to label this star. We're going to try to show that. All right, and so, well, now we're in the hat version, and so there's actually some more flexible TQFT structures available in the hat version. So to show star, what we're going to do is we're actually going to use Sutured Floer homology. We're going to use a Sutured Floer homology TQFT due to Juhas. This is his construction. So to prove star, we use Sutured Floer homology. Okay, so what Juhas's construction, he takes a sutured manifold, M gamma. What is a sutured manifold? This is a 3-manifold with boundary. So M is an oriented 3-manifold with boundary, I'll just say. And gamma, this is a set of oriented 1-manifolds in the boundary. And so what is the canonical example? This would be like a knot complement. So, oops, I've already messed up. So a canonical, like the example we'll care most about would be you take S3, you take a neighborhood of a knot out, And this gives you a 3-manifold with boundary, and then you need to decorate it with some sutures. And the sutures are, so this is a collection of embedded 1-manifolds. And so what we would normally do is we would just add meridians of the knot. That's sort of the standard construction. And we would add a pair of meridians of a knot. So this is a knot complement with 2 sutures on the boundary. And so to a sutured manifold, András associates a group, or a vector space over F2, the sutured Floer homology of M gamma. And this is just a vector space over the field of 2 elements. And so with, let's call this M sub k, so this is not to be confused with X sub k. This is a 3-manifold, just the knot complement decorated with 2 sutures. So as an example, the sutured Floer homology of MK, this is isomorphic to just the knot Floer homology of K. This is defined by Ozsváth and Szabó, and this is, I mean, basically just, they're exactly the same. Like, they're both defined using Hegard diagrams. The diagrams you use are the same for these 2. So this is sort of the motivating example of what we're, of sutured Floer homology for this talk. But it can be more general. It doesn't have to be knot complements. There's more general constructions. And in general, sutured Floer homology, you should think of this as a hat flavor. Like, it generalizes the hat flavor of Hegard Floer homology or knot Floer homology. But in general, it's not as useful for the plus flavors or the minus flavors, the ones where you have this U action. But we kind of get this information, we can kind of cheat and use it in this case because this Floer HF plus of T3 is rank 1. This is sort of the key that allows us to just use this simpler version of Hegard Floer homology. Okay, so András Juhász has a TQFT for these, which is somewhat analogous to the, which is fairly analogous to the TQFT for Hegard Floer homology, the original TQFT due to Ozsváth and Szabó. There's a notion of cobordisms between sutured manifolds. So we have this is more data than just a closed, just a 4-manifold with boundary, with 2 boundary components. Instead, this is a tuple, W, Z, C. So a cobordism from M1, gamma 1 to M2, gamma 2. This is a 4-manifold W, an oriented compact 4-manifold. Let me say W, Z is a 3-manifold. So the boundary of W is equal to minus M1 union Z union M2. So we think of W as having sort of horizontal and vertical boundary. I'll draw a picture in a second. And Z is a 3-manifold embedded in the boundary. It's a codimension 0 submanifold of boundary. And Xi is a positive contact structure on Z. And we want the dividing set of Xi to be these sutures. So if you remember from contact geometry, whenever you have a contact structure in a manifold with boundary, as long as the boundary has some sort of generic requirement that it's convex, you'll get these dividing sets. And so we sort of want to encode dividing sets geometrically into this contact structure. So we want it to have dividing set gamma 1 union gamma 2. And so well, the only example we'll need is for knot cobordisms. That's the thing we're going to be interested in. So for an example, as an example, this would be a link cobordism or a knot cobordism. So what we want to do is we want to take y1, k1, a cobordism from y1, k1 to y2, k2, k2. Let me put a knot in here. Well, it's a surface contained in a four manifold. So it's a pair consisting of a four manifold, a surface, and then also a dividing set on the surface. So it's a collection of arcs that run from one boundary component to the other. So divide the manifold into two pieces. What is the context structure? Well, so let me not say W, let's say, well, let's just say, or W is fine. So this will give you a sutured cobordism. You remove a neighborhood of the surface, and then the Z part is sort of the boundary of the surface. It's the boundary of a neighborhood of the surface. And then the contact structure is just the S1 invariant contact structure associated with the dividing set A. So this is the S1 invariant contact structure. Okay. So the concordance maps that I talked about earlier are examples of this. You can define them this way using, and so I kind of suppressed it, but these are also cobordisms between decorated knots. So we really want an even number of base points on each link component. And those have to be respected by this dividing set. So that sort of is a very reasonable notion of a knot cobordism. And so there's basically two examples that we need. And this comes down to the technical heart of this whole project. So the first example is the identity cobordism. So the identity cobordism, what is that? That's just, let me just say theorem. So this is due to Juhasz, is that the identity cobordism, I'll tell you what that is. The identity cobordism induces the identity map. So let's say this will be I times M. That's the four manifold. And then we'll have I times the boundary of M. That's the Z part. That's sort of the horizontal boundary. And then we'll have on here I times boundary of M. We just want to put the I invariant contact structure. So I'll just say CI. So this is a cobordism from M gamma to M gamma. And so in Juhasz's construction, he proves in his paper on these sutured cobordisms, he proves that the identity cobordism induces the identity map. Right. Fairly, I mean, conceptually, the proof is very simple, right? Like these Sutured Floer homology maps are defined by handle attachments. For the identity cobordism, you do no handle attachments. So the identity map. Very simple. So, but that's not quite helpful for our purposes. Instead, what we need is a variation on this. So this is due to Juhasz and myself. This is the recent work. What we actually want is, well, what we want to do, this is the identity cobordism. We can actually think of this as a cobordism between, you don't have to think, so you can take this four manifold and you can change which ends you identify as the incoming or outgoing end. And so basically, we're going to show that like the identity cobordism, now in quotes, induces the identity map also in quotes. But what I'll phrase it differently, I'll say the trace cobordism. So it's the same four manifold with boundary. It's I times M. Let me just write it down here. It'll be I times M boundary, I times the boundary of M, and then also the same contact structure. But now I don't want to view it as M gamma to M gamma. This will be M gamma disjoint union minus M gamma, and now it goes to the empty set. And we just assume, we associate to the empty set, the empty sutured manifold, we associate the sutured Floer homology is F. It's just the ground field. And so this is the trace cobordism. I mean, I could call it the identity cobordism if I wanted, but sort of the trace cobordism just bent over. And so the theorem that we proved is that this induces the trace map, the canonical trace map. Trace map. And I'll tell you just briefly what that is. So that's sutured Floer homology of M, tensor sutured Floer homology of M gamma minus M gamma to F. Let me just quickly tell you what that is. Basically, the sutured Floer homology of minus M gamma is canonically isomorphic to the dual of the sutured Floer homology of M. So sutured Floer homology of M gamma, minus M gamma is canonically isomorphic to the sutured Floer homology of M gamma dual. How does this work? Well, if you have a sutured diagram, or sorry, sutured manifold M gamma, and you take a sutured Hager diagram, sigma alpha beta, then you can take a diagram minus M gamma has a sutured diagram H equals sigma beta alpha, and with the same orientation. And so basically, if you have a disk from X to Y, X to Y, so if you have a holomorphic disk from X to Y, then on this diagram, you canonically have one in the opposite direction. It's also from, I mean, it's sort of here, it's going from here to here, but then in this picture, it's like del of Y has this component of X. So it sort of switches, just changes it to the dual. And this is a very common structure in Hager-Floer homology. So this is sort of the technical heart of the argument of the whole process. This is the hardest theorem, this trace formula, because you can imagine, like the identity cobordism has no handles. But this is sort of the trace cobordism. From here to here, I mean, there are a lot of handles. So you have to sort of deal with that. And that's technically very challenging to do. But that sort of is that's the hard part of the work. The rest on this concordance surgery just sort of follows from this mostly formally. So anyways, how does this tell us, how does this give us this concordance surgery formula? Well, there's one more thing that I need before I can, there's one more step, one more property of sutured Floer homology that we need to know before we can write down the proof. We're pretty close to the end. And that's, if I take a 3 or 4 manifold with boundary Z, and I have a contact structure on the boundary, C is a contact structure on Z, well then WZC is a cobordism from the empty set to the empty set. Or it could be that, from the empty set to the empty set. It's a cobordism from the empty set to the empty set, and the sutured cobordism map at FWZC evaluated on 1. Let me just draw a picture. So this is Z, and this is W, and we have a contact structure on Z. This is just equal to the map defined by Ozsváth and Szabó, the hat map for W evaluated on the contact element in hat of C, in Z. Depict the orientation of C, right? But I'm not going to get into that. And so the way Ozsváth and Szabó's map, you pluck out a ball, and then you have a map from Z to the ball. HF hat of S3 is sort of identified with F2, which HF hat of S3 is the same as HF hat of the empty set. So this is sort of the relation that we have between this sutured Floer homology and these invariants defined by Ozsváth and Szabó. Or this is one relationship. And so now we can kind of put the pieces together and prove this formula up here about the cobordism map on the hat flavor evaluated on the contact elements And so, well, I'm going to draw this picture. Let me. Oh, I guess one thing I forgot to mention is that I don't have a lot of time left, but oh, I guess I have enough time to say everything coherently. Before I tell you how to compute it, I just want to tell you one more component, which is sort of something you might expect if that you might expect. But one final component that Andras and I did was that we constructed a version of we constructed. So this is I'll just say this is you, Haas, and myself. We constructed a version of Sutured Floer homology. We made a variation on Andras's original construction, which is twisted by a two-form, twisted by a real two-form, twisted by two forms on the cobordisms and on the sutured cobordisms and three manifolds. And this is a fairly standard construction. This follows from similar to the original construction by Ozsváth and Szabó. We just adapted their construction to sutured Floer homology. And that means that if you have a, maybe I'll just say, if you have a omega on W, so this is a two form on a four manifold, and let's say that W is in a sutured cobordism like this, M1, gamma 1, 2, M2, gamma 2, then there's an induced, we call this sutured cobordism as the calligraphy W. So if we have a two form, then we'll get a map FW, and it's FW twisted by the two form from the sutured Floer homology of M1, gamma 1, and then we need to twist by the restriction of the two forms, sort of a standard thing. M1, we get a map, and these are modules over the Nabokov ring as well. Sutured Floer homology of M, gamma M2, gamma 2, omega restricted to M2. Okay, so we have this sort of formal construction where we have a twisted map, a map twisted by a real two form. All right, so now we can get to this computation of these torus complements. So we're going to take, so we have S1 times S3, that's this outer thing I've drawn, and then what we're going to do is we have our torus, and so let's just say this is our torus TC, and what I want to do is I just want to cut this into pieces in sort of a way that's convenient. So for the point is that in sutured Floer homology we sort of have two types of boundary. So we have horizontal and vertical boundaries. So I can kind of cut it in a way that creates corners and still compute the map. And so what I want to do is I want to cut it, let me actually draw, this will have like some non-trivial concordance part. So let me use some colors. The green is where we're cutting it. Okay, and why did I add an extra layer here? Well, what we're twisting by is we want to, the two form is a point times a Seifert surface. So it's a point in S3 times a Seifert surface, so I can just kind of put the two form into one of the slices. So this will be the identity, disjoint union, let me not use red. So the cobordisms we have are, we have the cotrace, which is the trace turned around. And then we have this trivial, these two trivial cylinders, but one of them has this two form in it. it has a point times a ciphered surface. So this one has sort of a non-trivial cohomology class. It's the identity, the Floer manifold is the identity, 2 copies of the identity cobordism, and then we have a 2 form, which is eta equals, or let's say omega equals point, or the Poincare dual of a point times a ciphered surface. And then here we have this cobordism map. We have the identity on this side, and then we have this concordance. I'll just say C. We have the concordance, and then down here we have the trace cobordism. Okay? And so now it's just a matter of computing what this composition is. As I said before, we can do these as a composition of sutured cobordism maps from the empty set to the empty set. And as I mentioned before, that composition is going to be exactly the, that'll be sort of like this side, the composition of the sutured cobordisms, and that will give us exactly the Sutured-Floer map evaluated as contact element. And so the co-trace map, now it's just pure algebra. It's just pure algebra. We have 1. We're going to start up here. We have 1. And now we're going to map it to the tensor product of HFK and HFK dual. And so by the co-trace, that's just the sum over a basis of not Floer homology of X dual tensor X, or maybe I'll put star. So let's just say we're going to sum over a basis of these elements. And so that lives in, maybe I'll use some green for the slices here. This element lives in the Sutured-Floer homology of this slice. And then basically all this is, when we have this twisted map, this 2 forms just supported on the interior of the 4, well, yeah, it's supported on the, away from the boundary of this. It's supported away from the sutured boundary of this sutured cobordism. But if you think about what this map is, basically from the definition of the Alexander polynomial, this just sends this element to X dual tensor X times T to the Alexander gradient of X. Let's say up to an overall factor of T. It's just sort of, basically if you just think about what it is, that's the, sort of the, if you just kind of work through the definitions, this ends up just being the definition of the Alexander gradient. And then what we're going to do is then this maps down, we just evaluate this cobordism on this element, and we get the sum of X dual tensor X, or sorry, tensor, the concordance map, FC of X, T to the Alexander gradient of X. And now, well, we're going to take the trace of this. So that means the canonical trace is like we take X tensor Y, and it's X evaluated. So it's this component of the tensor product evaluated on this one, the canonical map. And that gives you exactly the Lefschetz number of T in the variable T of this concordance map. That's just sort of the definition of the Lefschetz number. So, and this is now an element in sutured Floer homology of the empty set, twisted by the 0-2 form. But that's just, so this is just the Nabokov ring. And so I guess the things that I was promising to say is that that gives us this relation that the cobordism map for this concordance complement is equal to the concordance map for the unknot complement glued up times the Lefschetz number. And then also, trivially, this also gives you that the map on hat for the unknot times S1 complement is also 1, because we see that it's non-zero, right? So we see that it maps the contact element to the graded Lefschetz number of HFK hat of the unknot. So it's 1. So it's non-zero. So in particular, this algebraically gives us the, as we said before, this we just include this equation into HF plus and use this fact that the torus, HF plus of the torus twisted by a non-zero 2 form is just rank 1. And so that gives us the full computation. Anyways, I think that's all I have to say. Yeah. The actual Lefschetz, I mean, we've been using the maps to study concordances. And we do have some, we have some but not particularly the Lefschetz number. I mean, there's certain things you can say, for instance, like if you take a slice knot and you factor it through the unknot, and then you go back to the slice knot, then that sort of factors through, the map factors through the unknot, so it's going to be, the Lefschetz number will just be 1. So you can say things like that. I don't know if the Lefschetz number itself contains like some geometric information about like, surfaces in the complement of the, or anything like that. We haven't figured that out. But in general, the maps do contain geometric information. Yeah. Yeah. Oh, yeah. So, I mean, it's the Lefschetz number basically satisfies the same relations as the Alexander polynomial. Like, it's a symmetric polynomial, and its value on 1 is 1. So basically, like if you look at the graded Euler characteristic of HFK hat, you're basically taking a complex for HF hat, and then you're evaluating, and then you're weighting the different generators of the complex differently. But if you forget about the weighting, then you just get the Euler characteristic of HF hat. And it's similar here. If you forget about the weighting, you basically just get the Lefschetz number on the normal cobord is a map for the interval times S3. So that's just 1. You have 2 surfaces, and that's right. Yeah, I guess that's true. Is there an easier way to see this? I don't know. There's also some peripheral data too. Like you have some parameterization of the boundary. So because you have this contact element. So there's some, but yeah, I don't know. That's a good question. Yeah, certainly the tori that you get by gluing up ends, right? But yeah, that's a good point. I don't know if it's easy to do otherwise.